the last lecture we considered a deterministic finite state automaton. A deterministic finite state automaton, when you have a tape like this, the input is kept on the input tape and it starts reading the leftmost symbol in the initial state, and at any instance if you have a symbol A being read in state say Q, depending on Q and A the next move is uniquely determined. So, the delta mapping, which is the transition function, is from K into sigma into K. In a non-deterministic automaton, when you have a state and a symbol, you have a finite number of choices for the next move. It can move into say Q1, Q2, Q3, a finite number of choices. So, the mapping for a non-deterministic automaton is from K into sigma into 2 power K or power set of K, subsets of K. Okay. So, this is the definition of a non-deterministic automaton. If you want to realize a finite state automaton, it can be realized as a synchronous sequential circuit. Deterministic automaton can be realized as a synchronous sequential circuit, whereas non-deterministic automaton is a conceptual thing, because you are going to try out all possibilities in a simultaneous manner. So, it is an abstract machine. So, coming to the definition of non-deterministic automaton, it is defined like this. A non-deterministic FSA, it is a pi tuple M is equal to K sigma delta Q naught F where K as usual is a finite set of state, is a finite set of states. Sigma is a finite set of input symbols. Q naught in K is the start state, F contained in K is the set of final states and delta is the transition function. Delta is a mapping from K into sigma into the subsets of K. Now, we have to define what is the language accepted and how transitions can be represented. Now, before going into that, let us take an example. look at this state diagram. You have 3 states Q0, Q1 and Q2. Q0 is the initial state and Q2 is the final state. The transitions are given by this diagram. The language accepted will be a string of A's followed by a string of B's. So, you have a string of A's followed by a string of B's, such a string will be accepted, and this is a non-deterministic diagram because in state Q0 if you get a you have 2 possibilities, either you can go to Q0 or you can go to Q1. In Q1 if you get a B, either you can go to Q1 or you can go to Q2. So, this is basically a non-deterministic state diagram of a machine. You can draw the state table also. So, let us see how a string say A, B, B can be accepted. Starting from Q0 you have 2 possibilities, Q0 and Q1. From Q1 you cannot proceed further. So, Q0 and Q1, Q0 and Q1, possibilities are Q0 and Q1. Now, in Q0 you cannot get a B. So, from Q1 if you get a B you can go to Q1 or Q2, Q1 or Q2. So, after reading the whole string you can be in Q1 or Q2. If one of them is a final state, you accept the string. So, the sequence of states which lead you to acceptance is this. This is the sequence which leads you to acceptance. Now, let us define formally the accepting, how we define acceptance. Extend delta to delta cap. Delta cap is defined from k into sigma star into 2 power k. Instead of k into sigma we try to extend it to k into sigma star. How do we define this? Delta cap q epsilon is equal to q for all q in k. What does that mean? If you are in a state q and you are not reading any symbol, you are continuing in the same state. Okay. If you are in q and you are not reading any symbol, you are remain in the same state. That is what it means. Then for a string x belonging to sigma star and a symbol a belonging to sigma, what does delta cap q comma xa mean? This is a set. Okay. This set of states starting from q, after reading xa, what are the possible states in which the machine can be? This is what is denoted by delta cap xa. How is this defined? This is the set of states P such that for some state R in delta cap qx, delta of Ra contains P. The set of states P such that for some R in delta cap q of x, delta of Ra contains P. What it really means is starting from q, after reading x, you may be in a set of states, one of them can be R. Then from R after reading A, there may be some possibilities, one of them is P. So, it denotes the set of states P such that after reading x from Q, you are in a state R, and after reading A from R, you can go to P. All such possible states are in this set. So, this is the way delta cap is defined. Now, what can you say about delta cap Q of A for a symbol? This is the same as delta of Q of A, that is starting from Q after reading A, what are the symbols, what are the states you can go to, that is the same whether you use delta cap or delta. So, in this case also you need not distinguish between, while writing, between delta cap and delta, does not matter. Whereas next one more thing we will see, in that you have to distinguish between delta and delta cap. Now, you can extend this to 2 power k into sigma star, map this, that is we can say that delta of P comma A is a single symbol, P is a set of states. Okay. We can since we need not distinguish delta between delta and delta cap, I will rather put it as PW, where P is a set of states, is union of Q belongs to P, delta of Q W. When you want to extend it to a set of states, that is from a set of states P, after reading W, what can be the set of states in which you can be in? Take each one of them and find out and find the union, that is what it means. In essence, if you have some W like this, initially you can start with say some Q1, Q2, QR. After reading W, what can be the set of states? From Q1 find out the possibilities, from Q2 find out the possibilities, from Q3 find out the possibilities, and so on. The union is denoted like this. Now, what is the language accepted? The language accepted is denoted by T of M, where M is the machine. It consists of the set of strings W belongs to sigma star, and starting from Q naught, delta dash Q naught W denotes the possible states in which you can be in after reading W starting from Q naught. This should contain a final state. If delta Q naught W contains a final state. This denotes a set of states, at least one of them should be a final state. In that case, W will be accepted. if delta of Q naught W has one final state at least, then W will be accepted. The language accepted contains such strings. So, going back to this one, you see that starting from Q naught, after reading A you can be in Q naught or Q1, after reading 2 A's you can be in Q naught or Q1 and so on. So, these strings cannot be accepted. After reading A, B you can be in Q1 or Q2, Q2 is a final state. So, A, B can be accepted, A, B also will be accepted because one of them is a final state. So, the language accepted here will contain strings of the form A power n, B power m, n m greater than or equal to 1. Let us consider one or two more examples and then see whether the power is really increased. Can a non-deterministic FSA accept something which is not acceptable by a deterministic FSA? That is not true. Whatever you can accept by a non-deterministic FSA, you can also accept by a deterministic FSA. The set accepted is called a regular set. So, the power of non-deterministic FSA is the same as the power of a deterministic FSA. And how do you get this? You want to simulate a non-deterministic FSA with a deterministic FSA. The proof consists of that. Before that we will consider one or two more examples. So, look at this non-deterministic diagram. Q3, Q4, and the transitions are like this: 0 1, 0 0, 1 1. So, what sort of strings will be accepted? The alphabet here is 0, 1. What sort of language will be accepted? You can have any zeros or ones, you can read any 0 or 1, but it should end up with 2 zeros or it should end up with 2 ones. The language accepted will consist of such strings. In the sigma star notation, this will be 0 plus 1 star, 0 0 plus 1 1. This is called a regular expression, we will come to that in a moment. So, this really means any string of zeros and ones, and it has to end up with a 0 0 or 1 1. So, that is what it means. Now, this diagram or a finite state automaton is basically non-deterministic in nature, because starting from Q naught, if you get a 0 you have two possibilities. You go to 0 and again here. If you get a 1, you can go to Q naught or Q3, two possibilities are there. So, basically it is a non-deterministic state diagram. Let me draw the state table for this. This state table, there will be one column for each symbol and one row for each state. Look at the state diagram. From Q0, if you get a 0, you can go to Q0 or Q1. If you get a 1, you go to Q0 or Q3. From Q1, if you get a 0, you go to Q2, you cannot get a 1. From Q3, if you get a 1, you go to Q4, you cannot get a 0 here. So, the table will be like this. From Q0, if you get a 0, you go to Q0 or Q1. From Q0, if you get a Q1, you go to Q0 or Q3. From Q2, you cannot get anything, you cannot go anywhere. From Q4 also you cannot go anywhere. From Q1, if you get a 0, you go to Q2, you cannot get a 1. From Q3, if you get a 1, you go to Q4, but you cannot read a 0. Initial state is this, Q2 and Q4 both are final states. So, the state table will be written like this. You can see that in each compartment or each cell you have a subset of the set of states, whereas in a deterministic diagram you will have only one state there. This is the state table. Now, let me draw another diagram. There are 5 states here and Q0 is the initial state, Q2 and Q4 are final states. Is this diagram deterministic or not? From Q0, there are 2 arcs leaving with label 0 and 1. From Q1, there are 2 arcs with label 1 with 0 and 1 with label 1. Q3, 0, 1. From here 0, 1, from here 0, 1. If in any state you get a symbol 0, the next state is uniquely determined. If you get a 1 also, the next state is uniquely determined. So, what can you say about this diagram? It is a deterministic FSA. Now, what sort of language will be accepted by this deterministic FSA? You can see that starting from here, if you get 2 zeros, it will be accepted. If you get more zeros also, it will be accepted, right. So, anything ending with 2 zeros will be accepted. If you get a 1 here, again you go back here, and if you get one more 1, it can be accepted. So, starting from here, if you get 2 1s, it will be accepted, any number of 1s also can be accepted. If you get a 0, you go back here, but one more 0 you can accept. So, anything ending with 2 zeros or 2 1s will be accepted. So, this is a deterministic automaton which will accept the same language. And in this case, in this example, it so happens that both are having the same number of states, but when you want to simulate a non-deterministic automaton with a deterministic automaton, the number of states will be increased. Let us see how we can do that. So, we have this result theorem. if L is a set accepted, it is a language or a set accepted by a NFSA M, then L can be accepted by a DFSA M dash. M dash is equal to K dash sigma delta dash Q naught dash F dash. If L is accepted by a NFSA, it can be accepted by a DFSA. DFSA by definition form a subset of NFSA, is not it? So, if a language accepted by a NFSA can be accepted by a DFSA, what does that mean? They are equivalent. The language is accepted by DFSA and the family of languages accepted by Deterministic FSA and the family of languages accepted by non-deterministic FSA are equivalent. They are called the regular sets. They are called regular sets. Now, how do we find out what is K dash and how do we define F dash, etc. Now, K dash is really the subset, all subsets of K. So, if you have 3 states in the non-deterministic automaton, you can have 2 power 3 8 states in the deterministic automaton, and the set Q naught, the subset having Q naught alone corresponds to Q naught dash. The initial state is the one which corresponds to the subset containing Q naught alone and F dash corresponds to all subsets having at least one final state. Of F of M, that is F, at least one state from F, one state from F. Now, we have to, so a subset of states is usually denoted by Q1, Q2, Qk, where each one of them belong to F, K. This subset corresponds to a single state in the deterministic machine. In the non-deterministic machine, this corresponds to a subset of states. In the deterministic machine, this subset will correspond to a single state, and that is denoted by Q1, Q2, Qk. Note that to denote a subset we are using flower brackets. When it becomes a single state in the deterministic automaton, we denote a square bracket, and delta dash is defined like this: delta dash of Q1, Q2, Qk, comma A. This is defined as P1, P2, PR. Note that this is square bracket. From this set, after reading A, you go to this state. From this state, after reading A, you go to this state. If delta of Q1, Q2, Qk A equal to P1 comma. Note the difference. This is flower brackets, this is square brackets. From this subset of states in the original machine, if after reading A you go to this subset, in the deterministic automaton you define it as from this state, after reading A you go to this state. So, we have to prove that the language accepted is the same. Before proving that, let us take an example and convert it into the deterministic automaton. So, the one which we have considered we will take again. Maybe I should go back to the diagram. We have considered this earlier. This is a non-deterministic machine. Let us construct the deterministic machine equal. We have already seen what is the deterministic machine equivalent to that. By this construction, how do we get that? Let us see that. So, first let us draw the state table. The state table is like this. From Q0, if you get a you go to Q0 or Q1. If you get a B, you cannot go to anything. From Q1, if you get a B, you go to Q1 or Q2. You cannot read a. From Q2 you cannot read anything. This is a state table of the non-deterministic diagram. This is the initial state and this is the final state. Now, converting into the deterministic diagram, you have the same number of columns, one corresponding to A, one corresponding to B. The initial state is Q0. This is the initial state. So, from Q0, after reading A, what can be the set of states in which you can be Q0 or Q1. So, this will be Q0 Q1. Please note that to denote it as single state we are using square brackets, whereas as a set it is denoted by flower brackets. And after reading B, you cannot go to any particular state. So, this is empty. This is a subset of the set of states. Empty set is also a subset, right. Now, this empty set you will see that corresponds to something like a dead state. Now, afterwards you take this Q0 Q1. From Q0 Q1, after reading A, what can be the set of states in which you can be in? You have to find the union of this, that is again Q0 Q1, Q0 Q1, and after reading B, what can be the set of states in which you can be? Find the union of these two, that will be Q1 Q2. So, with this you have seen what are the next transitions. Of course, empty set we have to see. So, empty set means our next transition will be only empty. Now, we have seen for this, we have to see for this Q1 Q2. If you are in Q1 Q2 and if you get a, the next state is the union of these two, that will be empty. if you get a B, the next state will be the union of this, that will be Q1 Q2. So, we have considered this, we have considered this and so on. So, we need not prolong the table. Even though 2 power 3 8 states are possible, you can have an empty state, one corresponding to Q1 Q0, one corresponding to Q1, one corresponding to Q2, then Q0 Q1 Q1 Q2 Q2 Q0 Q2 also you can have, Q0 Q1 Q2 you can have, but they will not be useful and at this stage the table is complete. So, you need not have to proceed further. Even though 2 power k states, that is in this example 2 power 3 8 states are possible, only 4 will be useful. So, if you draw the diagram for this, it will be like this: Q0 Q0 Q1 Q1 Q2 and the empty state. The transitions will be like this: A, B, 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 A, B. You can see that this is exactly the same which we considered earlier. The earlier case, without naming the states, the diagram was exactly similar, but I think we used a D symbol for this, Q1 for this, Q2 for this, Q0 for this, and the transitions were exactly the same, right. So, you can see that this is a deterministic diagram, because from here if you get a you go here, you get a B you go here, from this if you get a you go here, you get a B you go here, from this if you get a you go here, from this if you get a B you go here. This corresponds to the dead state, the empty set corresponds to the dead state. So, using this construction we have converted the non-deterministic automaton into a deterministic automaton. The diagram, if the earlier one which you consider was like this. Now, what are the initial states? The initial state is just the one containing Q0 alone, and in the original diagram Q2 was the final state. So, any subset among these, this is the only subset containing a final state. So, this will be made as the final state. So, if you write it in a token form, this is the final state. So, this is to illustrate how you can convert a non-deterministic automaton into a deterministic automaton using this construction, and this is known as a subset construction. Usually we call it, informally we call it a subset construction. It is not you are constructing the subsets, then this method is called subset because you are using the idea of subsets. Now, the proof, you have to prove that the automaton which you have constructed, the deterministic automaton which you have constructed accepts the same language as the original non-deterministic automaton. The proof is by induction on the length of the string, on the length of the string. NFSA, you are given an FSA K sigma delta Q naught F, and you are constructing a DFSA m dash equal to k dash sigma delta dash Q naught dash F dash. Now, this is a set of subsets, and we have defined delta dash and F dash. How did we define delta dash? We defined delta dash Q1, Q2, Qk A is equal to P1, P2, Pr if delta of Q1, Q2, Qk A is equal to P1, P2, yeah. And F dash is the set of states which correspond to subsets which contain a state from F. Now, use induction on length of string accepted. So, if you start from Q naught, delta dash Q naught epsilon, what can you say about this? This will be delta of Q naught epsilon. It will be equal to Q naught only. Here it will be equal to Q naught and it will be equal to Q naught here. And if you have, if delta of Q naught x is equal to, so for strings of length basis, this is a basis class, you consider strings of length 0 so if epsilon is in the language, it will be in this language and so on. So if it is accepted by this, it will be accepted that, it will be accepted by that and so on. If Q naught is a final state only, it can be accepted by the non-deterministic FSA and also by the deterministic FSA. Now we show that if delta of Q naught x is equal to, or in general you can prove like this, in general you can show that prove delta dash of P1, P2, PR x is equal to some Q1, Q2, Qj if and only if, I am sorry, this is square brackets, delta of Q1, Q2, delta of P1, P2, PR x is equal to Q1, Q2, Qj. Now if you take just x is equal to epsilon, string of length 0, obviously delta of P1 P2 PR epsilon will be P1 P2 PR, and so it will hold for this. Now assume induction hypothesis, assume the result holds up to strings of length n, then consider strings of length n plus 1. So, what can you say about this? Delta dash, say P1 P2 PR XA, what will be this? You know that delta of P1 P2 PR XA is by definition delta of P1 P2 PR X A. This is the definition of a deterministic automaton. But by this one, this is equal to Q1 Q2 Qj. Delta of P1 P2 PRX is Q1 Q2 Qj. Now the way we have defined delta dash, I am sorry, this is delta dash. By the way we have defined delta dash, what can you say about delta dash Q1 Q2 Qj? This will be equal to say some R1 R2 Rp if and only if delta of Q1 Q2 Qj comma A is equal to R1 R2 Rp. This is by definition. So, what can you say about this? This will be equal to say R1 R2 some Rp. But we have delta of P1 P2 Prx is equal to Q1 Q2 Qj, and delta of Q1 Q2 Qj, please note that they are subsets. A is equal to R1 R2. So, from this and this you get delta of Q1 Q2, I am sorry, delta of P1 P2 PR XA is equal to R1 R2 Rp. So, when you find that delta, you get delta of P1 P2 PR XA is equal to this, and delta dash P1 P2 PR XA is equal to this, and this is delta dash, and delta of P1 P2 PR XA is equal to this. So, this happens, this is equal to this if and only if this happens, and this proves the induction step. So, when you start with the initial state here is Q naught, here it is the single subset containing Q naught, and any subset containing a final state will be a final state here, there, the deterministic automaton. So, you can show that if a string is accepted by the non-deterministic automaton, then it will be accepted by the deterministic automaton and vice versa. So, the language accepted by both are the same, T of m is equal to T of m dash. So, thus we show that the power by using non-determinism is not increased here. Any set accepted by a non-deterministic automaton is accepted by a deterministic automaton. Such a set is called a regular set. So, this is the step we have considered. First we have considered DFSA, now we have considered NFSA. We will also consider one more thing called NFSA with epsilon moves. Even in this case the power will not be increased, it will accept only regular sets. So, and we will also define what is called a regular expression. All these are all equivalent, none of them have more power or less power. So, the way the proof will go is like this. You have NFSA, you have DFSA, you have NFSA with epsilon moves, and you have regular expressions. All are equivalent. So, what we proved today is only this portion, given an FSA how to construct a DFSA. In the next lecture we will see what is an NFSA with epsilon moves and how to remove the epsilon moves. We will see that given an NFSA with epsilon moves, you can construct an NFSA without epsilon moves, this direction will prove. And we will also define what is meant by a regular expression, and given a regular expression how to construct an NFSA with epsilon moves. Then we will also see that given a DFSA how to find the regular expression corresponding to this, which will prove the equivalence of all these four. So, we shall see it in the next class.